Friends, let us continue to discuss on the topic curved beams. In this lecture, we will solve couple of numeric examples to understand how the Winkler-Bach equation can be applied to estimate the stresses at the extreme fibers in the intrados and extrados of a curved beam with large initial curvature. We will take up an example which can be a section like this. Let us say this becomes the center. If you look at the cross section, it is a typical rectangle. Of dimensions 40 and 20, and this radius being 40, it is subjected to a force P which is 20 kilonewton. We need to estimate the stresses at A and B and also at another section which is at 45 degree C and D. So, the question asked is estimate the stresses at A, B, C, D. In all these problems, it is interesting to first know certain geometric parameters which are important to estimate the stresses. So, let us say this is my cross section, this is my plane OO, this dimension is 20, this is my centroidal axis, which is at the radius r. One can see the radius can be now estimated as 40 plus 20, 60 millimeters, and this dimension is 20, this dimension is also 20, and we know this is to be called as R1, which is 40, and this dimension is called as R2, which is 80. The neutral axis will be shifted with an eccentricity E, which we need to estimate. Let us write down certain parameters. So, R is 60, R1 is 40, R2 is 80, B is 20 and H is 20. It means the section is about 20 millimeter this way. It is very interesting that moment about the centroidal axis will be actually equal to P into R, which will create a moment which is going to cause tensile stresses in the extrados and compressive stresses in the intrados. Therefore, M in this case is positive. Let us talk about the calculations for the section AB. Section AB is located as shown in the figure here. Let us say the direct stress will be P by A, which will be compressive, which will be minus 20 10 power 3 Newton by cross sectional area 40 into 20, which gives me minus 25 Newton per mm square. Moment M at the centroidal line is actually equal to P into R, which will be positive because it causes tension in extrados. So, moment will be plus 20 into 60 by 1000, which is 1.2 kilonewton meter. We know that for a rectangular section, M is given by 1 minus R by A B natural logarithm of R2 by R1. Let us substitute for these values. 1 minus 60 by 40 into 20 and B is 20, natural logarithm of 80 by 40, which is 1 minus 1.097 minus 0.0397, which is a sectional property required to calculate the eccentricity. The eccentricity E is M by M minus 1 into R. So, minus 397 minus 1.0397 multiplied by 60, which is plus 2.291 millimeter, which indicates that positive indicates neutral axis will shift towards the center of curvature. Let us now calculate the stresses at intrados and extrados, the extreme fibers. The general expression sigma I intrados is minus m by AE HI minus E by RI, which is minus 1.2 10 power 6 by 40 into 20 into E is 2.291, which we just now calculated, multiplied by 20 minus 2.291. You see H is 20 by 40. We are looking for the point A, which is intradas, so 2.291, which is actually equal to minus 289.87 Newton per mm square. Negative indicates it is compression. Sigma extradas will be m by AE HO plus E by RO, which is 1.2 10 power 6 by 40 into 20 into E, which is 2.291, 20 plus 2.291 by RO, which is R2, which is 80, which gives me plus 182.43 Newton per mm square. Positive indicates it is tensile. Now, the total stress let us say at A, which is an intradas point, is the direct stress, which is compressive, and the stress due to the moment, which is also compressive, which gives me minus 314.87 Newton per mm square. Stress at the point B, which is extradas point, the extreme fiber on the outside, this is the direct stress, and the stress due to moment is tensile. So, the net stress is 157.43 Newton per mm square. This is compressive and this is tensile. We need to also work out the stress at one more section CD, which is located at 45 degrees. Let us go for section CD. So, now section CD is located at 45 degree. The load is applied here, the R is known to me, the moment here is known. So, M along AB is known to me, which is 1.2 kilonewton meter. Therefore, M along the line CD will be this moment of cos 45, which is 1.2 cos 45, which will be 0.85 kilonewton meter. Now, I also want the force normal to this, which I say as P normal. I have this force, which is P. Therefore, P normal will be again P cos 45, which will be 20 cos 45, which is 14.14 kilonewton. Now, let us work out the direct stress, which is minus P by A, which is minus 14.14 into 10 power 3 Newton divided by A, which is 40 into 20, I get minus 17.675 Newton per mm square as compressive. Stress at interdas point is given by sigma I is minus m by AE HI minus E by Ri, which is now equal to minus 0.85 10 power 6 by 40 into 20 into E, which is 2.291, and HI is 20 minus 2.291 by Ri, which is 40, which gives me a value of minus 205.32 Newton per mm square compressive. Sigma at the extrudas point is given by plus m by AE HO plus E by RO. RO is as same as R2, which is now positive 0.85 10 power 6 by 40 into 20 into 2.291, 20 plus 2.291 by 80, which gives me plus 129.22, which is tensile. Therefore, the total stresses at C, which is sigma C, is minus 17.675, that is the direct stress compressive, minus 205.32, which we already have from here. Which is negative 222.995, which is compressive. At point T, which is sigma D, which is extrudas, the direct stress is same, but the stress due to moment is 129.22, which is plus 111.545, which is tensile. So, friends, using the equation derived in the last lectures, one can estimate the stresses at intradas and extradas points for various application, including the direct stress and the stress due to the moment. One can also easily conclude what is the nature of stresses. 1, based upon the sign convention, 2, based upon the nature of the moment caused on the curved beam. Interestingly, let us compare these results with the approximate equation suggested by Wilson and Kurian. Wilson and Kurian gave stress correction factors for both intradas and extradas. To know this, we need to compute R by H value. For our problem, this is 60 by 20, which is 3. If you look at the table back for a rectangular section, Ki, the stress correction factor for intradas is 1.3, which I gave you in the last lecture, and for outer it is 0.81. Now, the general stress can be simply m by I into h, that is the distance of the fiber, into the correction factor. So, if you really wanted to compute sigma I, then I should say this is going to be equal to stress at A, which is due to the direct stress due to the moment 1.3 times of m into 20 is the h value divided by I. Let us compute the I value for this section, which is 20 into 40 cube by 12, which is 1.07 10 power 5. So, therefore, let us compute sigma A, this is at intradas, which is minus 20 10 power 3 by 40 into 20, that is the direct stress compression, minus 1.3 intradas compression. So, 1.2 10 power 6, that is the moment, and 20 is the distance of the intradas fiber from the centroidal axis divided by 1.07 10 power 5, the moment of inertia, which I will get this value as minus 316.59, which is compression at the point A. Friends, let us compare this with the value what we got for sigma A, which is 314. So, I can compare the actual value what we got from Winkler-Bach equation is minus 314.87 Newton per mm square. Similarly, let us do it for sigma B, which is minus P by A plus 0.81 into 1.2 10 power 6, the distance of extradas fiber 20 mm by I value, which is 10 power 5, which is minus 20 10 power 3 by 40 into 20 plus 0.81 times of 1.2 10 power 6 into 20 by 1.07 10 power 5, which comes to plus 156.68 plus indicate it is tension. When we compare this with the results of sigma B, we can very clearly see this is 157. So, Winkler-Bach gave me the value as plus 157.43, which was very close to what we have from the approximate solution as well. So, this is how one numerical can be easily solved using the equations what we derived in the last set of lectures. We will take up one more example, which is slightly interesting and applicable to an offshore structure. Let us say example 2, a 10-ton crane hook is used to lift an object during commissioning of an offshore deck. Find the stresses at the intradas and extradas compare this value with the straight beam equation. So, that is the problem given. Let us say the problem is interesting because the section is actually a crane hook which has the geometric center as indicated, and this radius is 70 millimeter. We want to compute the stresses at 2 points A and B when this is subjected to a load of 10 tons. The cross section of this looks like this as a trapezium section. So, this becomes my OO axis now. I need to locate the CG. This becomes my CG. These dimensions are given as 120. This is B1 as per our nomenclature, which is 90. This dimension is actually B2, which is 30. Let us say this is R1, which is actually equal to 70, and this is R2, which is actually equal to 190. This is my R, which I need to calculate because I have to first compute this distance CG from the base. The neutral axis will have an eccentricity E. This is my neutral axis, which need to be computed for this problem. So, the first step is to locate the neutral axis, that is to find x bar, that is the first step. So, x bar can be computed as sigma A x bar by sigma A, first principles. So, this is my section, this is 90, this is 30, and this is what I call as x bar. Let us say divide this into different pieces, say this is piece 1, piece 2 and piece 3. So, x bar will be now equal to half base height, because this height is 120 into 1/3 of 120, that is my x bar of the piece number 1, There are two such pieces, piece number 1 and 3 has the same dimension plus the rectangle which is 30 by 120 whose centroid is 60, the whole divided by the complete area which is half h a plus b, which comes to be 144 10 power 3 plus 216 10 power 3 by 7200, which gives me x bar as 50 millimeter. Let us write down the value here. This value is 50. Therefore, R will be now 120 millimeters. Now, the second step is going to be to compute M and E for this cross section. We know M is given by the expression what we derived in the last lecture, 1 minus R by A B2 plus R2 B1 minus B2 by R2 minus R1 of natural logarithm of R2 by R1 minus B1 minus B2. That is the equation what we already derived in the last lecture for a trapezoidal section. Let us substitute for our problem. R is 120, A is area 7200 mm square, B2 is 30 and B1 is 90 millimeters, R2 is 190 and R1 is 70 millimeters. Substituting, M is 1 minus 120 by 7200 30 plus 190 B1 minus B2, that is 60 divided by R2 minus R1, that is 120, natural logarithm of R2 by R1 190 by 70 minus 60, that is B1 minus B2. So, this gives me M value as minus 0.080. Therefore, E as we know is M by M minus 1 into R. So, minus 0.08 minus 1.08 into R, which is 120, which indicates a positive value of 8.89 millimeters, which indicates that positive sign indicates neutral axis shifts towards center of curvature. The third step is to compute stresses. We know stress at interdas is given by minus M by AE HI minus E by RI, and stress at extradas is given by plus M by AE HO plus E by RO. RI is nothing but R1 and RO is nothing but R2. Interestingly, the sign convention for moment. We already know that In this case, look at this figure carefully. This will create a moment of this nature which will try to open out the ring. It means this will create tension in intradas and compression in extradas. But our general convention is moment should cause tension in the extradas. Okay. Therefore, applied moment now will be considered negative. So, applied moment is negative. So, m is going to be minus 100 kilonewton into r in meters. So, which is going to be minus 12 kilonewton meter, negative due to moment causing tension in intradas. We can also find the direct stress. Look at the figure. I have a hook and it is pulling, therefore, this is going to cause tension. The direct stress will be now positive P by A, positive because it is going to be tensile, which is going to be plus 100 10 power 3 by area of the trapezium, which is 7200, which is going to be plus 13.89 Newton per millimeter square, which is tensile. So, let us try to find the stress at intradas, which will be plus 13.89 minus, my m is negative, therefore, minus area into E 8.89, then 50, that is distance of intradas minus E 8.89 divided by R1, which is 70. Can please see this figure. R1 is 70 and this surface is the intradas and the distance of that is 50. That is why we have taken 50 here and 70 here in the equation. So, now this value will be equal to plus 13.89 minus minus plus 110.10, which gives me 123.99 Newton per mm square. Positive sign indicates it is tensile at the intradas. Let us talk about the extradas, which is going to be plus 13.89 plus minus 12 10 power 6 by 7200 into 8.89. HO is 70 plus E 8.89 divided by 190. You can look at this figure. R2 is 190 and HO is this distance, that is distance of the extradas fiber from here, this is HO, which is 70 because 120 minus 50. So, substituting we get plus 13.89 minus 77.84, which is minus 63.95 Newton per mm square, which indicates it is compressive at extradus. If I use the straight beam formula, which is simply m by I into y, let us compare this. To do this, I must compute I value. Let us say this is my section, this is 90, 30, this is 120, and the CG is at 50. I divide this into two parts, 1, 2 and 3. I is second moment of area, let us compute this. So, 30 is this distance into 120 cube by 12 by 36, that is for the triangle, plus AK square, area is half into 30 into 120, K is going to be 40 minus 50, the whole square of 2 pieces, plus for a rectangle BD cube by 12 plus AK square, 30 into 120 is the area, K is going to be 60, that is 120 by 2 minus 50 the whole square. So, I get this value as 7.92 10 power 6 mm4. Let us use sigma A m by I. So, plus sigma A, the moment is causing at the point A tensile stresses, 7.92 10 power 6 into 50 plus P by A, because P by A is tensile stress all the time, which is going to be 12 10 power 6 by 7.92 10 power 6 into 50 plus 100 into 10 power 3 by 7200, which gives me plus 89.65 Newton per mm square tensile, and in the extradus it is going to be compression into 70 plus P by A, which gives me minus 92.17 Newton per mm square compressive. If we compare these values, what we have from the actual value, so the Winkler-Bach equation gave me sigma A as 123.99 tensile. You can see here that is sigma A. Similarly, sigma B is minus 63.95. So, Winkler-Bach equation gave me sigma B as minus 63.95 Newton mm square compressive. So, there is a significant variation between the straight beam equation and the Winkler-Bach. If you do not use an appropriate equation for curved beams to find out the stresses in the extreme fibers in the intradas and extradas, the design can go wrong. So, summary, we did two numerical examples. Showed how the Winkler-Bach equation can be readily used. We have also compared the results with straight beam theory. The difference is significant. We also compare the results with stress correction factors suggested by the researchers. The results were close to Winkler-Bach. So, in these examples we learned how to use the sign convention for two things: one for the moment, two for the stresses. We have also learned if E is positive, it means neutral axis is shifted towards the center of curvature. So, friends, hope that with these 5 lectures on curved beams, which we have discussed on beams with small initial curvature and large initial curvature, one will be able to estimate the stresses for any kind of a curved beam with different cross sections whose m value and E value are derived and now they are known to you. Thank you.